scientists went hunting for the self in the brain. Like, where's the you that feels like you? It came up empty. There's no little guy in there. No CEO sitting in your head making decisions. What they found instead was a kind of void. A beautiful, mysterious void, where all your thoughts, emotions, and sensations arise and dissolve. It's like trying to find the leader of a jazz improv session. It's just a dance of interactions with no central conductor.
Space, the universe, everything in space as being represented by this giant network. And so what are the things in this network? The things in this network are what we can think of as atoms of space, these kind of point objects whose only feature is that they're distinct from each other. These atoms of space are related by this network that says this atom of space is related to these other atoms of space. That's kind of that's kind of the data structure of the universe. And the really surprising thing, the first really surprising thing is you say, well, okay, if you have zillions of these atoms of space and you have this network and it's being continuously rewritten as pieces of it follow these rules and change into other pieces of network, what does that look like when you've got 10 to the 100 atoms of space? What is the aggregate behavior of such a system? Well, there's an analogous problem when you think about a fluid, for example. You've got all these molecules bouncing around, and you ask, what's the aggregate behavior of all the molecules in a fluid? And we know, well, that's fluid mechanics. It's the equations of fluid mechanics, the Navier-Stokes equations, and so on. So the question is, what's the analogous limit of this graph being rewritten and so on? Well, it turns out the analogous limit is the Einstein equations. So the equations of space-time that you're very familiar with, that's kind of the first big clue that something interesting is happening, is you're kind of inexorably dealing with the fact that from that microscopic structure of just atoms of space and rewrites and graphs and so on, you end up getting the Einstein equations. And we can see a lot of detail, actually. We have decent simulations of things like black hole mergers. Black holes are very convenient because a really tiny black hole that is just a small number of sort of atoms of space across, so to speak, a really tiny black hole behaves in the same way as a big observable black hole. And so we can kind of do something where we're kind of just simulating these really tiny black holes and we can see them merge and produce gravitational radiation and all sorts of good things like that. That's kind of a notion of what space is. There are then questions about relativity and how relativistic invariance occurs, things like that. This is a slightly deeper rabbit hole. But the key idea is you've got this notion of space. Space is this hypergraph that's laid out with all these atoms of space. Time is the inexorable rewriting of that hypergraph by these computational rules. But the thing to understand is, what does an observer like us observe of what's going on in the system? Remembering that an observer like us must be embedded within the system. We are part of that system. And the thing we realize is that all that we can observe is the causal relationships between these updating events. So one way to think about it is, imagine that we were not being updated. Then whatever's happening in the universe, we're not going to know what happened. We're only going to know what happened when we've also been updated. So in a sense, what ends up being the case is that all we can really be sensitive to is this network of relationships, the causal relationships between updating events. So for example, let's say you have this little update that happens and it produces a certain output. Well, then you can ask, well, what other update events depend on the output from that first update event? And from that, you can build up this causal graph of what affects what. And it's that causal graph that is the real sort of substance of what's going on in these models. And that causal graph is, in a sense, a graph that connects both space and time. These events, one can think of them as, in the end, we will perceive them as occurring at certain places in space and time. And what's happening in this graph, the graph is the only sort of reality to the system. And the question is then, how do we parse that graph as observers? And what ends up happening, so key fact about us as observers, there are many things about what goes on that depend on our nature as observers. So one thing about us as observers that's not obvious is that we can parse the universe as consisting of states of space at successive moments of time.
When you say parse the universe, you mean to measure the universe. We can make observational
we observe the universe. We understand the universe to consist of, there's this state of space at this moment in time, then there's another state of space at a subsequent moment of time. So in our everyday experience, that's what happens. If you look around the room, maybe you see something that's 10 meters away. Well, the light from something 10 meters away gets to your eye in a microsecond, but your brain takes milliseconds to process that signal. And so to you, all the photons arrive simultaneously from all the photons from your local environment arrive, as far as you're concerned, in a blink of an eye, so to speak, in the time it takes neurons to respond. So for your brain, it's as if there is a state of space at a certain moment in time, and then there's another state of space at a subsequent moment of time. Now, in your day job, so to speak, you're dealing with things that aren't 10 meters away. You're dealing with things that are, 10 to the 25 meters away or something, 10 to the 26 meters away. And when in that case, this kind of idea that we have that there's sort of space separate from time and we can just think of an instantaneous state of space doesn't work anymore. It wouldn't work for us if our brains worked a million times faster than they do and we were still, living in rooms the same size as we live in now. Then we would be a brain, like a piece of digital electronics, that can see the photons, that it will see the individual photons, and the fact that we will decide to think of space as being this, the state of space at successive moments of time, that's a feature of the particular scale we're at and the particular characteristics we have as observers. It's not, in a sense, the intrinsic nature of what's going on.